I want to start stream. Okay, welcome guys. I think we are live. Let's check it. We should be live. Then let's open it. Let's see it. Yeah, we have a new microphone. Okay, good. Good. So today we will talk about, so first of all, long time no see guys. I was very busy preparing to these exams, so I couldn't manage to do always every day is a stream. However, I have finally decided to do it today, because it's weekend, because I can somehow allocate my time to do this stream, and I really want to dive into the graph neural networks. And I have heard many times about them from other people, from the internet, from blog posts, but I haven't really that much care about it, and I really didn't know the real use case of that. So today, let's try to implement the graph neural network, the simple network, the vanilla graph neural network. So vanilla stands for the simplest, basic, fundamental addition, fundamental fundamental stuff. So I'm thinking about trying that one, fundamentally small, simple stuff, and then using GAT v2 and understand how they work, and then understand what is the thing that it is better than our traditional neural networks, and why. And our question is that when we as a programmer, as a developer, should take care about implementing with graph neural network over the traditional neural network. That's a plan for today. So let me try to my notebook quickly. So because I might forget, guys, I might forget. So first thing is that when graph neural networks are better than traditional neural networks. Why GNN are famous? Okay, I set it down. I have a milk to drink. Weather is awesome. It is 7:08 a.m. in Korea. Weather is cloudy, raining again. But our how can I say? But it is raining outside. But we are inside. It is sunny. It is happy, and we want to study and we want to push our boundaries. Let's go. So okay. So let's go to fun, and then what do we have here? I forgot. Okay, I think we should go to نقشلي بشكل. Okay, نقشلي بشك, and then ls. Okay, mkdir gnn cd gnn. Okay, you as a viewer, you might be two types. You can come from two sources. First, from live stream, or second is from recorded video, like in the future. If you see me in the future, don't hold back to watch this stream in 2x speed or even 3x speed, and don't hold back to write comments at the time. And when you write comments, you can just highlight the time and then write to make it more concrete. I think we should increase the font size, right? Then, because this is not relevant to our problem. This is not relevant to our problem. So we don't care about this stuff for now. All we need is this guy now. Okay. So GNN, it is graph neural networks. That's right. Networks. So let's brainstorm what we what like who created this and when it's created, like history, right? Background. I need about background. I want to know about background. Who, when, why, where, how created this network. Okay. Second thing I want to know is what led to this discovery? What observations led to this discovery? Okay. Third one. I mean, current status? Current trend in GNN? Current trend. Okay. We are good to go. So now graph neural networks are okay. We have here. Wikipedia is quite good. Inputs are graph. One prominent example is molecular drug design. Wow. Okay, we have questions, right? We have questions. Background. So let's understand first about background, and then we can dive into the implementation. Background will not take that much time. So no, okay. I understood. Okay, we have different graph. We have graph attention networks. We have graph convolution networks. Message passing layers. Oh, we have a paper here. Can I read it? Oh no, access. What is this? It shows the visitors. Oh, I see. If you guys interested in this one, we can log in. Maybe we should save it. Okay. Oh. Visitors map. Counter map. Okay, we have 2 viewers. Good. Okay, I visit this link. It is closed. Gentle introduction. Let's see how gentle is it. Guys are everywhere. Yep. Okay. Basically speaking. Okay. What is graph neural network? It's a new network. It's just simply a network which works on graphs. Done. What is ANN? What is ANN, or what is let's say ANN, or traditional network. So it works on what? It works on images, numbers. Like images means just metrics, right? It works on metrics. But GNNs, we have a graph. It works on graphs. Okay, it's clear. So what is a graph? Does anyone know about graph? Graph. If you study it if you study the data structure, and usually if you go to the end of the data structure class, in the final lessons of the data structure, people cover these graph neural networks. Professor covers the graph. So graph is a set of nodes. It is set of nodes which might be connected in direct way or indirect way. I mean, indirect way, maybe I am interpreting in a bit wrong way, but direct way means we have nodes, right? They might be connected with each other. Okay, one node can connect to other nodes. Please, try to understand this. Don't hold back that much, and make sure that we have nodes, and they may connect to other nodes, to neighbors, to all other nodes, and this connection can be done in different ways. So this communication can be only one way, or it can be two ways. It's like a bridge, okay? Okay, if like we can paraphrase this like as nodes are city, and this way is bridge and roads. Okay, it is a bridge. Okay, it's a bridge which connects 2 or 3 cities. Imagine like that. And this connection, we call this connection as edge. Okay, edge is the way of connection between nodes. Okay, so basically you need to know these 2 things for graphs. Nothing more. I think nothing more. I don't like this page actually. Okay, so this is graph. It's clear, right? So let's try to now implement simple graph neural network. Okay, we need a data set, right? So what kind of data set we can use? So I need a good open source. I mean, I wish if there was a good paper. Images. Okay. We can represent images as a graph. That's cool. Or do you want me to go with this stuff? Let's try with simpler stuff. Oh, okay, it writes here, right? Like, what is edge? What is node? Number of nodes, longest length. Yes. But these 2 things are important. Most important things are these 2 things. Guys, we need a good stuff. Okay, we used to use this kind of stuff, right? Like, okay, this graph makes sense. This image makes sense. Oh, what is this? Okay, I want to try a simple one. Simple thing. Gated graph attention. What is this? No, guys, I am not editing anything. I think I found it, guys. Okay, we have one concurrent viewer. Okay, welcome. The last decade has witnessed an experimental revolution in data science or in machine learning. Okay, epitomized by deep learning methods. Indeed, many high-dimensional learning tasks previously thought to be beyond reach, such as computer vision, playing Go, or protein folding, are in fact feasible with a appropriate computational scale. Good explanation. Remarkably, the essence of deep learning is built from two simple algorithmic principles. First, the notation of representation or feature learning, thereby adopted, often hierarchical, features capture the appropriate notion of regularity for each task. And second, learning by local gradient descent type methods, typically implemented as backpropagation. Yeah, that was traditional things we used to do, and that's what most people know, and most people are like think that only this is AI. So here it's saying clearly that we have this notation of representation or feature learning, where we adopt in hierarchical way where we use this local gradient descent to do the backpropagation. So it's a traditional way. So while learning generic functions in high dimensions is cursed estimation problem, most tasks of interest are not generic and come with essential predefined regularities arising from the underlying low dimensionality and structure of physical world. This text is concerned with exposing these regularities through unified geometric principles that can be applied throughout the wide spectrum of applications. Okay, we cannot. They're saying in this abstract that there are many problems which are difficult to represent in high dimension, and therefore we can use geometric principles. It means graph neural networks, graphs, okay, to apply throughout the wide spectrum of applications. Such a geometric unification endure in the spirit of Felix Klein's Erlangen program served a dual purpose. On one hand, it provides a common mathematical framework to study the most successful neural network architectures. Okay. Wait, GNN? It gives constructive procedure, incorporate prior physical knowledge into neural architectures, and provides principled way to build future architecture yet to be invented. I didn't know about this guy. I don't know. Who is this? Mathematician, edition, educator. Erlangen. Flex Klein. Okay, new person. Felix. (1849, 1925). German mathematician. Okay, good. Peter. Scale blueprint of geometrical deep learning. I think, guys, you know algebra, right? You know geometry, so we can skip these things. Learning in high dimensions. What is high dimension? High dimension means images. High dimension means we can say it's text is high dimension. Is it correct? Let's prove. Let's check it. Inductive bias. I have heard so many times inductive bias. Inductive bias. You know what's bias, right? So for those who don't know, so bias is a term which is given to a person, which it is not fact, but which is based on an opinion. For example, if I say something like this drink is great, this drink really helps you to recover fast, let's say, but it's coming from my opinion, it's coming from my experience, from my opinion. It's not coming from an experiment, it's not coming from a solid proof, so it means bias. So inductive, so then inductive means what does the inductive stands for then? Rosenblatt is a famous guy who is the creator of this multi-layer perceptron. So here they are trying to convince us as a reader to say that to mention one important thing is that our world is not perfectly describable by this high level high dimension resources like images, and usually you don't have that much high quality data set. I mean, you cannot have a high quality images and describe our physical world or describe our nature or our language to a certain extent. So they argue that it's difficult. So what we should do to really cover all these representations, all these our real world things in details as a core. Symmetry is symmetry. I mean, if you draw x and y, if you draw x and y plot graph, and we can symmetry on y-axis or on x-axis. Isomorphism, optomorphism. Okay, I don't know. I don't know what they mean. Okay, hello, welcome to the stream. So basically speaking, let me to convince you also to go to the graph neural networks is because it's it is super difficult to express our core idea as a high level in high dimensional high dimensional data. For example, let's take an image. Do you know how big image in numbers and how big variety are there? I student or work in industry. Currently working in industry. So graphs so graphs on another way, on another hand, they can work on lower dimensions than high dimension, and they can better represent our problem, solve our problem. I mean, how we say that? I need to draw something. How can I draw here? Just wait. Open with viewer. Okay. High dimension, low dimension. Do you see how big is the freedom? And how small is the freedom compared to the high dimension? So working on low dimension is way better to understand the model, but working on high dimension creates this black box phenomena where you don't understand what the model is doing, and you cannot precisely control what it's doing and what represent to what in the inside of the model. So I mean, if you work with high dimensional images or high dimensional data, your freedom is big. Let's say it's X. But if you work on low dimensional, definitely this low dimensional X will be lower than X, okay? X high dimension, okay? This X high. So if you work on this problem, on this dataset, you can get it better. You may represent your problem better and solve it. So they are saying that we can work on this place using graphs as a neural networks. What kind of backpropagation are they using? I don't know. I have no idea yet. So we should clarify. Can't be changes to duplicate your... Okay, it doesn't matter. Okay. Okay, here's a blueprint. Simple logic. Geometric deep learning blueprint exemplified on a graph. A typical graph neural network architecture may contain permutation, equivalent, equivariant layers, computing node-wise features, local pooling, graph coursing, and a permutation invariant global pooling layer, readout layer. Okay, we pass a graph and we get a graph. We pass a graph, we get a graph. We pass a graph, we get a one node. Maybe this is pseudocode. Let omega and omega prime be domains. This beta asymmetric group over omega, and write omega prime inside. What is this notation? Comes from omega if omega prime can be considered a compact version of omega. Different settings. What kind of settings? Okay, here we are talking about graph. Okay, graph is a collection of nodes and edges. Okay, let me to write it down because it's very compact way. Okay. Where we is number of nodes, E shape, E is edges, and shape of V and V. Okay, this is clear, guys. Okay, this is clear. Another problem is that, okay, we have a graph. So in our traditional logic, we have y equal to weight dot x plus bias, right? So this idea comes from Rosenblatt, from multilayer perceptron. So what about how does this work in graph neural networks, in graphs? So that's a problem we need to fix. And then, as far as I know, these graphs, graph neurals, graph layers, let's say these graph layers, input, you give to this graph function your graph representation, and you pass edge indexes, edge indexing or something like that, and you will receive graph. Okay, we can say graph prime, something like this. So I want to know in this graph what's happening, and I think they're using backpropagation, right? Can they use another backward function to update the weights, if they have weights, of course? I'm pretty sure that inside these functions they should have like at least bias and weight, at least weight plus bias also. So let's keep reading. Okay, we did this one. Social networks are perhaps among the mostly studied examples of graphs. User edges correspond to the friendship. Okay. This is key point. Permutation. Permutation means mixing the order. Mixing the order of a set, or let's say we have an array of numbers. So permutation means shuffling these numbers between. Isometric. What is isometric was? Isometric, let's see. Same, isometric, isomorphic, having similar form, relationship. Let's check if I speak right or not. Okay, order, grouping, presentation, sorting. Okay. Okay, here they are explaining about permutation. Okay, let's say we don't have any edges. Okay. Node features as a row of n and d matrix. Okay, here it comes, the truth. Truth is that we should not depend on order, of course, but how we can present that idea of not depending on order. Okay, let me to make it more clear. So here, how we will send this graph to the function? Graph is abstraction, right? It's abstraction which we as a human understand better. If like social media, every node is a person, and the connection is a relationship, friendship, or between persons, right? So it helps us as a human to understand it better. But for a computer, for a program, how we can represent this graph? So this is one question. So answer is maybe straightforward. So we need to make it as a matrix. If we represent it as a matrix, it's very easy for a GPU and CPU and others is computational hardware to calculate. Okay, it's clear we should represent the graph as a matrix. Okay, another problem. What the shape of matrix should we like? Or in other words, what we should include, how we should include the graph to the matrix. Okay, and they are saying basically we need to stack node features as a rows of n and d matrix. What is d? D dimension. Okay. D dimension node wise. N number of nodes. we have a matrix, right? So let's have an example. Okay, let's have an example. You can see my screen, right? Okay, you can. Maybe I should remove this. Maybe I should remove this one to here. Let me to make it small. Okay, you can see it, right? If you don't see, if you have problem, audio or this image quality, let me know. Okay. Let's say I have a node. Okay. Okay, we have 4 nodes. Let's say we have 4 nodes, and we have connections between them. Like for example, we can say node 1. How can I say talks to? I can say node 0 talks to at index 1, 0 talks to at index 2, 0 talks to index 3. And I can say first node in index 1 talks to index 0. It will be bidirectional. And then 1 talks to 2, and then 2 talks to 3, then maybe etc, etc, etc. And then 3 talks to 1, to 0, let's say. So this is edges, okay? So I think it helps you to have a better understanding of representation of edge in action, in practice. So we can definitely draw it. We can definitely draw it. So now is that, as far as I understood, correct me if I'm wrong, is that we have a node, right? So we create this big matrix, okay? And where we have, you know, each row where, for example, here our node is our node is just like this, okay? And then node like this, vice versa. And then node -2. I mean, the order is changing, okay? Order is changing, and it repeats. And it repeats how many times? It repeats, I think, how many permutations can we do with 4 objects? It was like this, right? I forgot this. What was the name of this one? Guys, help please. What was the name of this this mathematical notation? I know it means 1 star 2 star 3 star 4 means 8 24. 24. That means it means we should have 24, right? Then we should have 24. Etc. Okay. So it's what they are saying basically, as far as I understood. Okay, we built matrix X. We have x1, x2, x3, x3, x4, x4, and etc, etc, etc. And each x is D. N means N. What is N? N is a number of nodes. What is D? Oh wait, if it is number of nodes, then it should be not like this, right? It should be 1, 2, or 3, 4 only. Okay, so there is something I'm missing, guys. The order of rows of H should be tied to the order of rows of X. Wait, what is F here? It's saying we don't need permutation. Does it mean like that? No, wait. I didn't get it. Adjacency matrix. Yeah, I have heard about this one. Adjacency matrix. It gives you basically the map, communication map of which nodes talks to which nodes. No. No. We should read it carefully again. Graphs and sets, okay. Hey, I am into coding since 2 years, and now currently I am in my 3rd year, and I am fully into backend Python, okay? And I have done 3+ internship from various startups. Okay, good. Now I really feel I should transition and should learn new things. Which will be best at this time? Congratulations, you did good job. 3 internship, and you are third grade in third year. You're doing good progress. You should just keep that way. So you say transition. So it means you get bored with backend of Python. You want something new. If you want something new, maybe you can go with agentic things, agent stuff. Or you can come to AI and do some AI stuff, AI papers implementation. That might give you some interest. Or try to combine, like apply AI to some kind of domain, or use backend plus AI to deliver better AI, to deploy better AI, like MLOps. We call it MLOps. You can use MLOps. Okay, let's read it carefully. I don't know. I am not getting it very well. So I understood that we need to make the graph as a matrix. But here's a question comes, how permutationally should it look like? So let's see. Okay, backend plus what? ML, AI, Web3. Okay, anything which you like. What would you like to do? Do you like images? Go with images and computer vision. Backend plus computer vision. Try to, like, how can I say, make computer vision projects, solutions, or try, like, in Web3. I don't know Web3. In Web3, what's the cool feature of Web3? So try with Web3 also. I mean, you have backend skill, so it means you can do backend. So try to maybe work with LLMs also. How can you deliver with backend and LLM? Just, I would say, don't hold back, and there is no ideal answer for your question. And you have intuition. Do with your intuition, I think. Yes, this is clear. This is clear. Next one. Okay, sure. Yep. Important thing is keep your momentum and always be positive, and always try to study, learn from people. I mean, I know it's easy to say this kind of words, but if you really experience that thing in your life, then you will feel it very, very, very deeply. What does that mean? I mean, yes, should not depend on ordering of nodes. Yes, this makes sense. The desirable property of that property that functions acting on graphs should satisfy is thus permutation invariance. Permutation means order, shuffling of the order. Invariance, guys, I need to check it. Invariance. Now, okay, invariance never changing. Oh, I see. It should never change. Invariance. Okay, we have 2 viewers, guys. Feel free to chat, write, and ask questions. If you have questions regarding this, some kind of word, let's say, what is isometric? Do you know it? Or like, feel free to write, and we should study. We should go ask. Don't feel shy. Feel like at your home. So permutation, it should be same. Makes sense. Okay, I can represent it as a matrix. So it means it will be node 1. I mean, then how it will look like? Wait. So permutation, it should be always same. Okay. If permutation should be same, then we have node, right? We have node, and in the node we have 4 values, and the order should never change. Okay. Domain omega equal to g, and the space xgrd is that d-dimensional node-wise signal. D-dimensional node-wise signals. The symmetry we consider is given by a permutation graph P sum of n whose elements are all possible ordering of set of node indices 1 to n. Oh, hello, Bleak. Yeah, welcome. Okay, let's talk about sets. Okay, where it is independently applied to every node and applied to some aggregate. Yes, makes sense. Guys. So very good thing. So how it will work is that, you know, we have this function, right? We pass to functions the graph, right? Graph output, and in this f, what may happen is that do dot product and aggregation for individual node, and then sum them to apply a global sum aggregation. Let's say aggregation. I don't know this one, but I took discrete mass before this stream show up in my YouTube feed. Oh, I see. Then if you take discrete mass, I think this makes sense, that quite easy for you. I think you can easily understand it better, like by like reading once. And if you have questions, write, ask, or if I'm saying some kind of, how can I say, things which might be wrong or unclear, ask, demand. I'm happy to change and try to explain it better way, or we can learn together. Okay, this theta, this notation applied to all, and this inner function is applied to individually. So that's how this our F layer looks like. Okay, this is clear. This is also clear. Okay, good. Okay. Are you PhD? No. I'm not PhD. I am not PhD. Do you know? Do you know what was the name of this symbol? I mean, it's exclamation mark in literature, but in mathematics, what was this now? This not one. It's used for statistics for permutation. Like we say, 2 and exclamation mark. It means 1 multiply 2 and equal to 2. So what is this name? So that's my small challenge for you. Like, I don't want to Google it. I know that, but it's like I'm not remembering exactly what was the name. But I really like the idea of this one. No, it's not factorial. No. But you are close. I mean, it's also this kind of advanced topic. It's not factorial. Or maybe factorial. Wait. You might be right. Factorial. Actually, I studied not in English class. Factorial. Maybe factorial. Yes. Yes, you are right. Genius. Good. Factorial. Okay, our x is our representation of graph as a matrix. We pass to the f, and here we get dot with matrix specified by weight matrix d by d. Two generators. What generators? Generators. Deep sets. Okay, I understood. Basically speaking, simply speaking, we have nodes and we represent each node as a row or as a value, as a vector or as a value, and then we apply a weight to that layer, and then we get output as a graph. So we should make sure that order should never change in the matrix. Then we say if we don't have the connection between nodes, if we don't have edges, we can use this adjacency matrix A, where if it's 0, it means no connection. If it is 1, it means on that place, U node and V node are connected. Okay, each node is a row of X. Yes. Mm-hmm. I don't know this one. Okay, I know there are a lot of things which we don't know, which we need to have a solid idea. So here, let's say we have this input graph, our input, our output, our layer. So we take this XB, XA, B, C, D, E, and apply to our function, this function, and then we will get a output of that one. Okay. Okay, that's the main idea. I think this is clear, right? This is much clear. It's time to code. Like, we need to write code. We are not a mathematician. We are not a theoretist guy. We need to practice. We need to practice, right? So in our example, let's say we have 4 nodes, right? Node 1, 2, 3, node 1, 2, 10, 23. Node, it's node 1, node 2, node 3, node 4. And maybe like connection is maybe like this. Connection is like this, connection like this. And this is input, okay? And in output, we will have same shape. But in output, this guy is depending on this guy, this guy, this guy, and this guy. So what does that mean? What does it mean? So there is some kind of function applied to 1, 2, 3, 4 values, and is a kind of non-linearity function or something applied, then it's written here on top of this guy. Basically like that. Does it make sense? Guys, does it make sense? For example, in this example, XB is connected to XA, XD, XE, XC, right? And in calculating the HB, the new graph from the previous graph, we are depending on XB, XC, XE, XD, XA. So we are depending on how many? Five nodes. So these 5 nodes are somehow talks with each other and then output this HP. So it means, let's assume we have a node as an index, okay? Let's say I have a 0.1, 0.5, 0.9, 0.3. Okay, we have 4 values, okay? Let's keep it, okay, let's keep it simple, 3 values. Or do you want only 2 values? No, I mean, let's go with 3. 3 is quite good. 0.1, 0.5, 0.9. We need 3 of them because our index is 3. Someone is screaming outside. Okay, this is our matrix. So it consists of information, okay? Node information 1, node information 2, information of node 3. So now let's make a connection, edge vector. Or no, I think it should be matrix, right? How can we represent edge matrix? Good question. So previously here we saw that we can use this adjacency matrix where we can put 1 when it's connected and put 0 when it's not connected. But what is the shape of A? It's n by n. 3 by 3 means. So let's try with adjacency. Adjacency. I think it's very old word. So it will be, you know, like, I think, let's say each column is a feature. Each row is also a feature. So it's like a correlation map, okay? Heat map. Okay, sorry very much. Sorry. It feels a little bit sleepy. So we should wake up, guys. No sleep. So here, this position means, okay, let's try like this. Let's say 0, 0, 0. 0, 0, 0, 0, 0. And then 0, 0, 0. Okay, this is our matrix, okay, guys? Okay, this is our matrix, basically. And if I set this one to 1, what does that mean? It means that node in index 2 at index 1 and node at row 0 are connected with each other. What does it mean? What it means that the 0.1 is connected to 0.5. If I set this one is 1, oh, if I set this one, it means this 0.5 can also talk to 0.1. And these two things means bidirectional. Bi means in both way. So if I set this 1, if I set this to 1, it means 0.1 talks to itself. How it can talk to itself? It can basically talk to itself. Just imagine like that. Okay, we can represent a adjacency matrix. So let's build it. So let's assume we need to have simplest possible adjacency matrix. So let's say first node is connected to 2 and 3. Second node is connected to 1 and 3. Third node is connected to 1 and 1. Okay. Where is my phone? Where is my phone? Okay. Okay, good. So what does it mean? What it means that our all three nodes are interconnected with each other equally. Okay. So if I want to build, so let's say this is input, okay? Input graph. And output, I think output, we need to define a function, right? So basically speaking, our graph in index 0 will depend on what? It will depend on, I think, itself. And on node at index 1. Index 2. And then another next one 0.5 Q what then? Q3, some kind of W plus no 0.1 plus W and itself 0.5 plus 0.9 W and one more 0.1 W plus 0.5 W plus 0.9 W. Okay. These ones are repeated, just repeated. Same. Okay. So here the question comes, what kind of W should it be? I mean, this W is global W or it is local? And what's the shape of the W? Now we are working in scalar format, right? We are going too deeply inside, but we don't want to go too deeply inside. We want to represent this whole thing as a matrix multiplication, matrix operation, basically speaking. So here, let's read this paper. Let's continue reading this paper. So we need edge matrix, right? So for edge matrix, if I don't mistake, we can use Euclidean distance. I mean, what does edge matrix tells? So it tells the relationship relationship or how strong the node affects to the target node. Because edge matrix brings a value, right? So it also brings a value. Oh, oops. Note that now the adjacency and feature matrices A and X are synchronized in the sense that the UV specified adjacency information between nodes described in the US rows of X. Yes, synchronized. Yes. Okay. Okay. Advocates for those that are also local, thereby the output on node U directly depends on its neighboring nodes on the graph. Okay. We are already representing that actually with using this logic. Oh, hop. Okay, we need to write it down, guys. Hop. I will write it down. Wait. General recipe for constructing a permutation equivariant function on graph by specifying a local function phi that operates over the feature of nodes and its neighbors. And the permutation equivalent of function phi apply phi neighbors in isolation. Okay. So if we need to use this local function, f or phi, let's call it phi. Okay, x1 means value of node, xn1, and we apply fee for it. I don't know what does it means, but I understood that our fee becomes independent because it doesn't care. It doesn't care what it's working with. It doesn't worry. It's not worrying about the order. In fact, it does. It does care. Group convolution, spherical convolution. I mean, we are going to the inside. Okay. Actually, I know what application, what code they use to build this one. Okay, this is our interesting section. Interesting section to read it, to study. I don't care. Okay, this is convolution. I think you all know. It's not that much fancy now. It's our old friend. Yes. Okay, it's the residual networks. Okay. I think here, we go to like this, and actually it will be, it should be like 0. One, 1, 1, 0, 1, 1, 1, 0. Okay. Okay. Mosquitoes. I see, I see. Uh, I don't care about these ones yet. We are not on that stage yet. So here we know that it can be all just linear layer for inner function, where W and B are learnable parameters, and we can use the same W and B make in that case. Okay, here we have example. It's good. Okay, guys, let's try to focus on like very carefully for this one. Okay, then we can. I hope then we can understand it, so that we can then go and dive into the code. In many applications of graph neural networks, node representation are not just arbitrary vectors but coordinates of geometric entities. This is the case, for example, when dealing with molecular graph, the node represents atoms, may contain information about the atom type as well as its 3D spatial coordination. Okay, node may contain atom information and it is positioned in 3D. Okay, we have a formula. Finally, guys, let's look to this formula. If you some kind of annotation, what some kind of notation, and in the function, if u f v and xu minus xv, this is norm. Squared norm. So you're saying this is distance. Between distance between fu and fw. If u f u. I have a good idea, guys. So here, main point from here, guys. Let's look to that formula. Where is it? Where is it? Where is it? Where is the formula? So this is formula of our graph layer. Done, guys. Done. But simply that's it. Graph neural networks. GitHub. Oh, we have this one. I think the best place is here to start. Okay, to recap again. To recap, we have a graph, and we want to output a graph. And when we want to output when we want to input a graph and output a graph, we call it message passing. And between when applying the graph, we can use these two functions for it. So we can find these two functions here. Okay, they create their own GNN. Maximum. I think it's considering the TIGT. I think it's working as a vector, I think. Okay, we have a X and H index. Wait. Okay, we have a X. It means edge, that big X, and or collection of edges, a collection of nodes. Sorry, node feature matrix of shape, number of nodes in number of channels in channels. Okay, our X is n by input channel. Something smells very bad outside. Maybe someone was frying an egg, they forgot that they are frying an egg, and that become dark egg, and that smells. Or some kind of potato sauce, maybe. Old potato sauce. And H index is 2 by n. Okay, so here 2 means we have only 2 row, and n means the number of nodes. 2 means only two row. Yeah, only 2 rows. If you have only 2 row, then what's the first row and what's the second row? Okay, see, guys, torch guys, very good, guys, community. So they're saying, okay. Oh, we have a code, guys. We have a code. It might be cheating, guys. Let's look to this one. It x index and hy weight. Previous ask get item. Hmm? Okay. Mm. Let's try this dataset. First of all, let's install the torch geometric. Torch geometric. Okay. Torch geometric. Really? No module? Oh, we have installed it, guys. Mm-hmm. Oh, my iPython is broken, guys. Sorry. Let's go just to Python. Geometric dot datasets, right? Datasets, import what? Import planetoid. Hmm? Look, we have edge index 2 and 9104, and we have a data. Data means, but why it's 9103 104? Okay, that's what data we need to handle. Edge index. Number of edges. Two, and how many number of edges? 1, 2, 3, 4, 5, 6. Edge attribute. Edge attribute. I mean, where is the adjacency matrix here? Okay, we have an example here. Wait. So our x is -1, 0 and 1. Okay, it is our information in the node, and then we can see 0 is connected to 1, 1 connected to 2. So 0 is connected to 1. So here 1, 2, 3, 4, right? Why it's 4? Why it's 3? Why it's 4? I mean, this 2 means starting index and ending index. Maybe 0 is connected to 1, 1 connected to 0, 1 connected to 2, 2 connected to 1. Okay. Makes sense, guys. Makes sense. So it means the length is, it can be as big as we can satisfy, as we can uncover whole connections. And we are considering bidirectional connection. Always bidirectional. Amazing, PyTorch. Thank you very much. PyTorch geometric. So thanks to this guys, we are quickly understood. Okay, well, it's already 2 hours. We are spending time, but it makes now much more sense. And what about edge weights? So this is adjacency matrix, I would say. Okay, we have benchmark datasets. Okay, we understood. So basically speaking, edge index is 2 by n or 2 by some kind of value shape matrix, where the first row shows the source node and sort node index, and the second row shows the target node, which are connected. And if we want, we need to represent this as bidirectional. So if 0 connected to 1 and 1 connected to 0, we need to write both of them. Let's go to our example. So then, in the end of the day, how does this edge matrix looks like? Target is 1. Source is 1. Target is 1. Wait. Let's say target 0, 1, 0. It's 2. 1. 0. 1. 2. 2. 0. 2 to 1. Okay, 1, 2, 3, 4, 5, 6. So our edge matrix in this case should be 2 by 6. I have also dataset, guys. This is our dataset. And now I'm saying no. Okay, that's our stuff. So are we so this is so this is a edge collection. So edges, and this is our dataset nodes. So now we need to apply some kind of linear function or iteration or convolutions, doesn't matter, to the x with respect with edge index. So what we can do in Torch? Let's go to here. So if we have FU and FV, we don't have this length between each other. So I think basically what we should do is to take a tensor we cannot take a dot product between H index and this X. I mean, they use this special H indexing format for specific reason, I think. So what is the reason? Maybe if I say, wait, sorry. If I say, let's say it's x, okay, it's x. Let me say it's as a e, okay. And if I do x e, so what is the shape of x? If we say it's 3,327, right? And 307,3703. So this is the length of each row. And this is number of nodes. So it means if I do something like this, it will work definitely. But I don't know whether it's doing these things on purpose or not on purpose. What? Too many? Ah, yeah. I understood. This is individual. This is shape of one node. I mean the information inside is one node. This is equivalent. Connection. Okay, it's normalized. So we need to apply some kind of function to each of them. Oh, it's here. Okay. Don't look to first one. Look to second one. Multiply inner function and then sum of them and add to the previous one and show it. So FC, let's say it's linear layer, right? Let's say it's linear layer. Linear. What is the input for linear layer? Input for the linear layer, let's think. Oh, it's tricky question. Tricky question. So basically speaking, we have 9104. I want to make it. Do I want to reduce it? Without that kind of fancy stuff. So it means this minus, and we take a norm and square. Oh, really? We don't have torch? For torch. What this function may be? Hmm. I mean, I can represent this one. So I expect the shape should be, you know. 9104. 9 something like 9104 and 3705. Okay, correct. So this is done, this is done. And multiplication between, okay, we give this one. Okay, let's create this small function. Ah yes, I forgot to add keyword def 1 2. So what we will do with that one? I mean, norm is what? Norm shows the distance, right? Norm shows the distance. The FU and FV are the source and target nodes. Okay. What we can do? We can multiply. We can add to each other. But what we should do here? Let's check. But why are we passing in norms then? Oh, error. So here we can say how was the annotation? Say FU, FV, and then linear layer I say 9104 9104. I have thought we can use something like this. It's not working. Okay. Something wrong. Okay, we have linear layer, and we pass through this linear layer. Oh, we need to have 3703. Really? Okay, we have this much row, we have this much columns, and then we need to do multiplication, right? If we want to do multiplication with z, we need to satisfy these column numbers. Yes. Linear layer, and then torch dot and then dot functional dot relu. Do we have this kind of thing? Do you have it? Oh yes, we have it. So we can do like this, and then we can use the same linear layer maybe, or maybe we can use another linear layer. For FV. Dot shape. Okay, now we have 9104, 9104. Okay, we lost the information. So it's bad because we don't want to lose information. Now we are preserving the shape, the order. So if we apply this one to individually, and I also use this one, I mean, I'm taking the linear layer from here, linear layer from here. I'm not using the norm, but this function asks norm. Where is this function? Where is this function sleeping? Where is that function? Where is that function? Guys, we are almost understood, guys, aren't you? Do you have questions? I mean, we use this one and apply and use some kind of linear layer with a non-linearity function for this also. What is this shape? You know, what is the shape of this guy? I wrote it right. Okay, the shape is this one, right? But I want the sum of that. If I use unsqueeze, maybe I will have one more dimensionality. Squeeze on 0. No, it doesn't help. So I want to say sum. But some in one direction. In what direction? Some 0? In dimension 0? In what direction? Direction 0 or in what dimension? Let's think like let's just think. We have one nodes and their values. And we have second values, second row, second nodes with their values. So we subtract. So if I use dimension 0, it means we are summing all these nodes together. If I use index 1, I am using all features, summing all features of a certain node. I think second one makes sense, but it's too big number. I mean, yeah, I mean it's not that big, but it's big anyway. So this function is a bit unclear, but some kind of function. But now we need to get a dot product of this guy and this guy. Oh no. This sum applies to all, right? It applies to all of them. We have this function, then we can use linear layer. We can linear layer, just linear layer. I think addition. For now, let's say it's just addition. And to the addition, I want to check if they fit, if they can be multiplied or not. I think yes, they can be multiplied. So they can be multiplied. So we can multiply them. But what about dot? I think if I just take dot product, but dot product won't work. We need to make it. Second one is transpose. Now we have it. x1 means what? X plus, oh, x1 means x plus out. Wait, out shape. Out shape, that changes. Shape of out is changing. So we should change that one. So we have x plus out x1. I mean, definitely we apply some kind of function here, okay, guys? Why we are stacking with these things? Maybe the problem is that maybe here it's not a dot product. Maybe it's just multiplication, but generally multiplication is bad. Okay. Our out should work with x. Yes, I understood. So we need to sum up in dimension 1. No, I think I made a mistake here. So here it's just number, right? It's number of features, and I already lost the first one and target one, so I need somehow reduce it. So I have E, right? I have still have E. So there should be some kind of transformation applied. Dot product, maybe, but there must be some kind of sum. So we need to reduce 9104 to 3327. Because there are duplications in the 9104, we want to remove the duplications. So yeah. Let's look to the data. I mean, let's look to the code. Cheat sheet. Let's look at this one. No, I don't get it. I don't get it. I don't want to read it. Mm-hmm. Dense pooling layer. Maybe aggregation function. Yeah, basically, we understood how can we represent, but we need to bring it back. The x1, the x1 should have the same shape as the x. So should when we apply this all transformations, x1 should preserve the shape. But in our case, it's not preserving. So there are functions, there are methods, and there are different methods. We can apply attention mechanism, we can apply convolution, etc. and etc. So let's check what people are doing. Message, okay, message passing. Okay, this is what we want. We want to make it a message passing, yes. Differentiable, permutable, invariant function. Okay. We have tutorial, good. Okay, new x based on x, yes. I think this is hyperparameter. We don't care about this one. Maybe. What is this? No, it's a function. It's function. It's not hyperparameter. It's a function. Denoted differentiable function. Multilayer perceptron. Okay, this is multilayer perceptron. We will apply multilayer perceptron. This is our previous x, and this one is another x. So it means I can basically fix this one. I have this one. We need to bring this guy. Let's use sum phi k differential function for this 3. I mean, differentiable function means multilayer perceptron is applied for each of them individually or not. I and j. We have I and j, and then e. Okay, I don't know. Like, guys, if you know, give hint, guys. Give hint if you know. So here, if I want to take xi, I cannot take xy, unfortunately, because the shape is different. So, and I cannot know the correspondence of it, right? So we can say what about if we apply linear layer? Special linear torch linear, and it will be 3703. Tick, ting, ting. mean, do we need to? Do we need to apply for whole? No. X E, right? And we have this shape, right? And I can just apply linear layer, guys. I mean, special linear layer. I don't care about 2 here. Linear layer equal to torch dot nn dot linear. Here 3703. 3703. But what's the output? 3703, I think. Linear. Okay, we have a typo. Linear. Okay. A special linear layer, and we apply X E. And let's check the shape. Okay, 291043703. Now we need to apply this differentiable function. So it will be sum in 0 dot shape. Okay, and then we have another multilayer perceptron. No, wait. So we fix this guy, right? We found this one. Now we have previous x and our previous x and our x. So what we should do is this, with these guys. I mean, this sum works, but shape is different with this x. I mean, here our sum should be much difficult, much stronger, much detailed one. Guys, what we can do, guys. I mean, in 9104, we can have, for example, node 0 connected to node 1, and then in next one, node 1 connected to node 0. So this whole thing should be summed together. I mean, like, they should be merged, so that we need to reduce this dimensionality. Okay. Let's say we don't have any torch. We have just Python. So what would you do? What would we do? In that case, we have repeatance, right? We have duplications. need to check shape. Yes. No, we cannot do it. We have 0 all shape, 1 and all shape. So we have repeatance here, guys. We have repeatance. If I do something like this, will it show me? Will it show me or not? Now what I want to do is that we have first row and we have second row. Let's see it here. Let's say 0 1, let's say 0 1 2 1 0 1. Okay, here we have 1 2 3 nodes, right? 0 node, 1 node and second node, right, at our index. But here our connections are actually only 3 connections, right? 0 1 1 0, and they are connected. So I want to reduce these things as a 1. So I want to check, like, switch the order of them. If it works, then it works. Okay, this order, right? It means not this one, right? It means, it means we should check every place, but on E, yes. Can I do equal? But it will not make it will not work, right? It will not work. No, I want to do 0, but here all. I'm confused, guys. I'm confused. Let's see the code. Linear transformation of X. I mean, maybe it's another things. GC. I think it's another implementation. Okay, here what they are doing. Okay, it turns out this is what we are doing. We have linear layer, output layer, edge index. Okay, row and column. Okay, degree. What is degree? Degree. Do you see somewhere as a degree? Degree utils. Convert to degree. You mean? Degree column x size 0 degree in square root degree norm column row norm. Because I got a norm of degree and they use edge index again and x and norm. Propagate. Where is the propagate function? Where is the propagate? Okay, we have propagate. Okay. Why it's so messy here? No. Okay, we are missing this norm. X, this one, and X. Okay, this core is propagate. Core is propagate. I am also doing propagate, but my out here was not same shape as out. So propagate, the key is in propagate. Okay, return out. Okay, we take a hook and message and aggregate forward hooks values. I think this is doing like calling to the neighbors and collecting the information from neighbors and aggregating it. Hook. Where is the hook? I mean, show me the hook. No. What we did? Where is the hook then? Interesting. I have never seen this kind of thing. Okay, it's everything is inside. Okay, I don't care. I don't care. I don't care. Does Python has a hook? Hook? No. Wait, hook is here. Aggregate forward hook. Mm-hmm. Message forward hook. Message forward hook. I mean, where is it? Where is it? Where is it? Where is it? Here it is. It's all ordered list. Ordered dict. And we are saving to there the ID in the integer to the hook. Where is the handle? What is this removable handle? So I think removable handle means we pass this hook order dictionary to the handle. It removes some kind of unnecessary thing, and it assigns the new ID, and it preserves the hook. Don't we have a better solutions rather than using this way? Okay. What is the norm of this E? Not register, not update, not message. Propagate. Where is propagate? Okay, here's propagate. Yes, it defines the connectivity. Yes. Size n by m. Yeah, here's a problem which we are facing is that, basically speaking, we have this guy, right? I applied the linear layer inside these two things, but now I need to eliminate the duplications occurred in this one, and then just some summation or maybe like mean values, and it will kind of fix it. But it's I mean it might be wrong also because I see they are using the norm. But I don't see here a norm. So they are finding a normalization. Okay, then what they are doing? They pass this norm to the propagate as a value of the h weight, I think. They pass x and they get just out. Done. And that's done. I mean, like, everything is inside this propagate for this case. And then if you want, they add bias, and then they will have output. This is how this graph neural networks works. I see. So what was our plan in before, in the start of the stream, and what we achieved till now? Let's recap. So when GNN are better than traditional neural networks. Okay, graph neural networks are better if we have a dataset which is low quality or noisy, and it is possible that we can represent as in low dimensional things or as a graphs. In that case, they are better to use, and they are lightweight compared to high dimensional data. Second question: why GNN are famous? Because they are brand new, and because we can apply convolution layer or linear layer or attention mechanism to the graph neural networks also. So therefore, it's also good. So then we figure out about Felix Klein. So Felix Klein is a mathematician, German mathematician, who was also kind of contributed a lot to these graph neural networks, basically. And then what we did, we figured out how to put the graph, represent as a graph. So each node of the graph is represented based on their index, and then we use adjacency metrics to show the connectivity between each between each nodes. And then in PyTorch we have the so great resource and great information about actual implementation of graph neural networks. And then basically that's it for today. For this stream, we failed to prove this formula. So I'm missing the norm, and I'm missing how they are. So basically, I'm not missing a norm. Finding norm is not big deal. I'm missing how to calculate this 9104. How my problem is that I want to reshape this thing into 3327 because there are many duplications. So I want to eliminate these duplications. So they use so in the code of PyTorch, I see they use this hook, and they use this H update forward hook, where if you look very carefully, you can see that they are using this removable handle, which handles the duplications, I think. That's it, basically. That's it for today. Have a good, productive day. It is 10:19 a.m. So if you have questions, write on comments. If you have any suggestions, I am always welcome to hear. Thank you very much. Thank you for joining. Okay, bye-bye. By the way, the background was a virtual background, and it is from Japan. So actually, outside weather is same as in the picture. Okay, bye-bye.